OK, so I'll start. So today I'm talking about a really basic problem in continuous function fitting. And this is the problem of trying to learn signals that have simple Fourier transforms. So the setup for our problem, I'll mention, yeah, my apologies. The paper for this talk is not online yet. It was intended to be online, but when you have 6 people on the paper, it's inevitable that it doesn't happen. So this will be online soon, so then you can see the results that I talk about today in paper form. So this is joint work with Chaim Avron at Tel Aviv University, Michael Kaprilov, my brother Cameron Musco, Amaya Velinker, and Amir Zandier. OK, so the problem we're considering in this work is a really simple problem. We see some continuous signal over a time. Let's think about it as a time interval from 0 to t. And we're going to take samples from that continuous signal and then try to figure out what the rest of the signal is. OK? We also care about the case when maybe our samples are noisy. So we just think there's like some fixed noise added to them, and we still want to get a good approximation to our signal y. So when I say a good approximation, what I want is that we find some y tilde that is close to our signal y over the entire fixed time range, 0 to t. OK, so the big questions you can ask when you want to solve a problem like this is computational efficiency and sample efficiency. How can I take as few samples as possible and still learn the signal? And once I get those samples, how can I actually learn y tilde and represent it in a computationally efficient way? So like the first thing is, this is obviously an ill-posed problem if I don't make some sort of assumptions about my signal. Because if my signal is just like very poorly behaved, it can jump all around, there's no reason to believe that the information at my samples gives me any information about the rest of the function. So we need to, when you solve this problem, make an assumption about y in some way. Either it's structured or it's smooth. And sort of by far one of the most common ways of putting an assumption on a continuous signal you're trying to fit in science and engineering is to make an assumption about its Fourier transform. So we don't talk about the smoothness of the signal itself or any direct properties of the signal. We talk about properties of the Fourier transform. OK? So probably the most common thing, which a lot of people have seen, is we assume signals are band limited. So in communications, we often assume that our signal only contains frequencies that have absolute value less than f. And it was constructed with those low frequencies. So this is like the standard thing you assume with analog to digital conversion for audio or in general when you're doing communication. And so how many samples under this assumption, roughly, can anyone tell me how many samples I usually require to recover the underlying signal y on 0 to t? Yeah?
Should be around the size of f, like f, magnitude f.
Yeah, so roughly what happens is, roughly for band-limited signals, you need to sample them at the Nyquist frequency, which will depend on f. It will be 1 over f is the frequency you need to sample at. And I'm trying to recover the signal on a range of width t from 0 to t. So roughly, I need order f of t samples. OK? So it turns out this is not a rigorous result. Nyquist sampling only works for like signals you define over the infinity. If you're actually trying to reconstruct signals on a bounded range, you need to do something more than that. But you can get f of t samples. And this was sort of first resolved in this classical work by Slepian, Landau, and Pollack in the 1960s, where they used these things called prolate spheroidal wave functions to figure out exactly how to interpolate band-limited signals on a fixed range. An important thing that we'll come back to later about that work is it doesn't actually do uniform sampling to recover the signal. To provably get order f of t samples, you need to use a non-uniform sampling scheme. OK, so that's one way to constrain your signal. What are other ones we're familiar with? In computer science, engineering, you often see sparsity constraints on the signal. You assume that it's represented as the sum of a small number of frequencies. So this is the standard setup in like compressed sensing, sparse recovery.
Question? Why,
yeah.
So with uniform sampling, that's not true?
You can do uniform sampling, but you lose a lot if you're not going to do, if you're doing it over a fixed range. You'll either lose like a quadratic factor or
Quadratic
if
and f.
quadratic and ft. You'll square ft. Or if alternatively, you could get a polynomial dependence on your accuracy epsilon. But neither of these is desirable. So if you want to get like ft plus, and I'm hiding
only
accuracy.
1 over epsilon is fine, right?
Yeah, but if we want to get log 1 over epsilon, which is possible, you need to do non-uniform.
Then,
Yeah, poly epsilon, you're fine to do uniform sampling. But we'll talk about, I haven't even defined epsilon. We'll get to the formal problem statement. Right now I'm sort of being loose when I say recover the signal y, and we'll get into what that actually means, what my accuracy epsilon means.
Just make sure, so
Yeah.
shall I think of t as a time period or something? Or?
Think of t as a time period, but it's also like really any continuous signal. So maybe you're thinking of, I'm a geoscientist, I'm trying to map how much water is in like a surface. So you can think of that as like a distance. So it's either time or space, but we think of it as one-dimensional, not Fourier domain. So for sparse signals, you generally require order k samples. And this, it's like easy to show in the noiseless setting, but very recently, there have been rigorous results that are extended to when you're sampling continuous signals in a noisy setting. The other thing we see in engineering quite a bit is multiband signals, and this sort of has the sample complexity you would expect when you combine sparsity and band-limited functions. You have to sample out what's known as the Landau rate, where you sum up sort of like the band limits for all of your bands. Okay, so those are sort of the standard constraints you see on signals in signal processing and in engineering. But I actually claim that this problem of putting a constraint on the Fourier transform is far, far more general than those problems. So in particular, we don't need to think of our constraint as allowing or disallowing certain frequencies like we did for band-limited or sparse functions. You can think of general sort of priors on frequencies. This would be like the Bayesian perspective to fitting signals. And what we're going to say is that a signal is we put a prior on the sort of power spectral density of a signal. So we give a number to all of the possible frequencies, and that number represents how likely that frequency is to appear in our signal. You can make this formal by assuming your signal is like a Gaussian process, and this prior is telling you the variance of all of the Fourier frequencies in that Gaussian process. But it doesn't matter, you don't need to worry about the details of that too much. It's very common to use Gaussian priors. It's very common to use exponential priors, or it's really a Cauchy-Lorentz prior where it has like a heavy tail. But for a reason we'll explain later, they call it exponential. Okay, so yeah, so for the prior distribution, you're assuming that this is a prior on your power spectral density. The reason it comes up a ton in science and engineering is because this is actually equivalent to when you assume a prior on your power spectral density to assuming a prior on what's known as the autocorrelation function of your signal, which is like the correlation between any point at time t and that point shifted into the future some distant z. So for like stationary signal, this correlation is constant across the signal. So this is the reason sort of these problems appear all of the time in science and engineering, because people love to use these autocorrelation priors. So autocorrelation priors underlie Gaussian process regression, if you've heard of that. Kriging is really the same thing, except that's what they call it in the geosciences. Kernel ridge regression and machine learning. In all of these cases, you're taking a signal and you're assuming it's generated by some random process, and you're putting a prior on its autocorrelation function. But we're not going to go through the details, but I'm just telling you that this is exactly the same as putting a prior on its power spectral density. If you put a Gaussian prior on the power spectral density, this is the same as putting a Gaussian prior on the autocorrelation. If I put a Lorentz prior on the power spectral density, this is the same as putting an exponential prior on the autocorrelation. So this is sort of the reason these problems come up all the time. Okay, so you have this very general class of problems. How do people usually solve them? Generally, what you see in practice is we sample things uniformly, because typically there's not too much guidance about what else you should be doing. So when people are solving Kriging problems in geoscience, they typically sample your space uniformly. It's the common method that's used, with some exceptions. So as I mentioned, we actually know that provably you can get better performance or better accuracy for fitting band-limited signals when you don't sample points uniformly. when you actually sample them with the density that is denser at the edges of your intervals than the center. So if you're familiar with like polynomial interpolation, it should ring a bell, sampling more towards the edges of the intervals, okay? This, yeah.
So under what error? Is it uniform error?
Yeah, well, there's gonna be under like a average L2 norm error.
So
You'll get
even-
better performance.
So even if you, it's even for average error?
Even for average error, yeah. So this is actually true for polynomials. Like, I think we usually think of uniform error, but I believe for fitting continuous polynomials, even to get average squared error, you need to do like Chebyshev node sampling.
What about L1?
I'm not sure.
Now, sparse here means what?
Sparse.
Sparse.
Sparse means it's the sum of k like complex exponentials, so sum of k sine waves. Yeah.
So Fourier sparse.
Fourier sparse, yeah. So we know we can do provably better for band-limited signals. Recently, it was established that you can do provably better for sparse functions. So remember I said I had that slide that said there's like some simple methods for doing sparse functions in the noise-free case. To get all that stuff to go through to noisy samples, you need to do non-uniform sampling. And then in practice, in some applications, it's sort of been caught on that non-uniform sampling is a good thing to do. Like if you see implementations of certain types of ultrasound where they try to acquire like Doppler signals from ultrasound to do blood flow in the ultrasound, they'll use non-uniform sampling strategies to try to acquire those signals. And there's some sort of like loose theoretical evidence for why that stuff works, but we don't have a good theoretical justification for it. And sort of the point of my talk today is that really for all of the problems I talked about, for any prior on your power spectral density, you should be doing non-uniform sampling. And in particular, we can show that there's a very simple complexity measure that measures how many samples you need to reconstruct functions under these priors. It matches up with sort of the expected sample complexity of all of these problems. And there's a universal non-uniform sampling scheme that matches this complexity up to logarithmic factors. So when I say universal sampling scheme, I mean it doesn't depend at all on what your prior is. It doesn't depend on what your function looks like. There's just a fixed function that has higher density near the edges of the intervals. If you sample by that, you can provably solve any problem in this class of power spectral density constrained Fourier function fitting problems.
So I have a question.
Yeah.
Trying to be adaptive would not help.
It's not clear that trying to be adaptive won't help. Like, certainly we don't have any lower bounds against adaptive algorithms. Yeah.
Wait, you don't have any lower bounds at all, or do you?
We don't have any lower bounds at all, but we have some lower bounds. Yeah, there's some rough reasons to believe why that complexity measure we get, you're not going to be able to improve on, which I'll try to touch on that later in the talk. Okay, and then not only is there a non-uniform sampling strategy, but there's a really easy method to recover your function from your non-uniform samples. It's actually just the standard method used in Gaussian processes. You solve a kernel-ridge regression problem. Okay, so the takeaway before I sort of get into the details, because this problem does take quite a bit of details to set up, is that essentially everything reduces to the sparse case. So the reason we're writing this paper now is because of those results I showed you from a couple years ago and from this year on getting provable bounds for approximating Fourier sparse functions on a continuous interval. What we've been able to show is that essentially all of the machinery from the sparse case can carry over to be very, very general and applied to any prior distribution. And we do that using tools from like random matrix theory and random linear algebra tools on sampling matrix problems. Okay, so this is how I'm going to formally set up this Fourier function fitting problem. I'm going to define a weighted inverse Fourier transform. So typically the inverse Fourier transform is I just have some vector g, which is values over frequencies, and it's going to combine a bunch of complex frequencies to output my time domain function, right? The weighted Fourier transform is really the exact same thing, except I'm going to throw that weight function mu, which is my prior on the power spectral density, onto the columns of my inverse Fourier transform. So the columns that have lower weight just get down weighted in that. That's how I define it. It's that linear operator on G. Okay? I'm going to assume that my signal can be written as inverse weighted Fourier transform f mu star of x for some signal x plus some noise term n. And this is just like, I'm not defining, the noise term is a fixed constant noise. I'm not gonna like put any distribution on it. I'm just assuming it's some vector of noise that's set ahead of time. And our goal is to find some efficient representation of a signal y tilde such that y minus yt is y minus y tilde is small. And by small, I mean it's less than a term that depends on, I'll define these norms in a second, an energy term on x, which is the underlying true Fourier transform, and constant times the size of the noise we added to our samples. Yeah?
So this Fourier transform, is it a Fourier transform, a weighted Fourier transform?
Yeah, it's a weighted Fourier transform.
No, but is it like a Fourier transform and then like there's a inversion theorem or?
Yeah, so it's a Fourier transform from like L2 space where your measure is mu to L2 space where your measure is uniform on 0 to t. So there's an inverse, but it's going between two different L2 spaces. Yeah. Okay, so by this norm t, all I mean is the average squared error of the signal. So that's the sum of the difference between the signal squared over the whole signal, just the average of that. By the mu norm, I mean that it's the norm under my weight function mu, or my prior mu. Okay? And so in this bound, we have epsilon in front of the x term, because we should be thinking of epsilon as a tunable parameter. In general, higher energy functions are harder to fit because they can jump around more crazily. So you need to take more samples to get a good fit for a high energy function. So our sample complexity will ultimately depend on epsilon. We need to take more samples, and that will let us drive down our error term that depends on the energy of the function. The term that we can't really drive down is the noise term. Like certainly I can't do anything better than c equals 1 because I have no idea what my true function was. I just have this fixed noise on it. So we don't care about driving that down. I'm gonna be happy with any solution that gets c to some constant. Like we'll be able to get it to equal 2. Yeah.
A question, like in the special case where noise is 0, is the problem easy, simple?
The problem is it's not easy because there could still be many x's that map to your same function, and you're sort of trying to find the one with lowest energy. So you still need to, yeah, in some cases it's simple. Like in the k-sparse case, it happens to be that you recover with exactly k samples, but in other cases you still need to have an epsilon term depending on.
For example, I can imagine say noise is 0, that will still be.
Say again?
For the talk, can I think?
You can think of noise as 0 for the talk, yeah.
Okay.
Yeah. Okay. So our goal is to find an efficient representation of a function y tilde that satisfies this bound.
Question?
Yeah.
So this x sub mu norm, I guess I went by too fast. Does it imply that the reconstruction will, if I look at it, will look similar?
Well, it's just a constant number. So like if you drive epsilon down low enough, then the reconstruction will be very small.
Okay,
Yeah. So we're going to usually get log dependence on epsilon. So think of this as like, you know, if your signal generator has some bounded power, it can't output an x with huge energy. So it will go down to 0. Yeah. Yeah. Go ahead.
So this setup doesn't capture the sparse case, right?
This setup captures the sparse case if you're careful about sort of like how you define measures and everything. I'm trying to deal with things as like if you were, I defined mu as a function, and then I was doing integrals over like d eta. If you define things as like integrals over the discrete measure of k to rack functions, you can get it to all go through for sparse functions. There's nothing sort of inherently wrong about sparse functions, but I'm just trying to do everything.
They're not defined as a prior in the same way as.
They're defined as a prior where it's like a uniform. So maybe this is a distinction. I'm not dealing with the case when you have your function I'm dealing with one fixed sparsity pattern. So you give me the sparsity pattern, And then my prior is that it's some uniform prior on that sparsity pattern. So we don't deal with the case of like trying to find the best function amongst all k sparsity patterns. There's some natural ways you can deal with this by doing like epsilon net arguments where you show I could just like do a grid search over all sparsity patterns. But like for what I'm doing today, it's just one fixed sparsity pattern.
So it is a continuous problem.
Yeah.
It's not
Yeah, exactly. Okay, so for bandlimited functions, this energy term is sort of like the natural term. It's the energy of the function in your band limit, the energy of the Fourier transform in your band limit. Okay, so I don't want to try to give you too much intuition for like the continuous prior case because there's just too much problem definition. The way you can think of it is that energy term will increase if I'm trying to use an x that puts more weight on an unlikely frequency. So to recover an unlikely function, I'll need to take more samples. You can set this up like formally in a Bayesian way, and you can show that the algorithm we get in the end outputs like a Bayesian map estimator for the problem. But just think of it as, in general, that energy term goes up if I want to use less likely frequencies, so I'll get more error for less likely functions. Okay, so this is my goal. There's one really simple strategy to solving this problem, and that is to convert it to a regression problem. So instead of trying to solve the recovery problem, let's just solve a L2 minimization problem, where I'm trying to minimize the distance from my true function y to f mu star g. So g is going to be what the Fourier transform I'm going to guess, plus an energy term that depends on the mu energy of g. Okay? If we can solve this regression problem to a constant factor, it's not too hard to see that the g we get out, I was saying the approximate solution, I guess I'm calling x tilde. The x tilde we get out solves our recovery problem with some constant that same constant factor c. So we can reduce everything to an L2 regression problem. Yeah?
Is the mu given to you, or what is the mu?
The mu we're thinking of is given to us.
Given to you.
Yeah, this is our prior that we chose ahead of time. Yeah. So just pictorially, this is what the regression problem we want to solve is. It's not like a well-defined problem because it's an infinite dimensional regression problem. But what it is we're trying to just find some g that has its weighted Fourier transform close to our true signal y. And then we're having an L2 penalty, or like a mu penalty on the signal g. And I claim that if we solve that,
Are the frequencies? The eta, whatever.
eta are the frequencies, and t is, yeah, so g is defined over frequencies, and then t
So
is.
presumably, if there's slop in the answer, you can get rid of the large frequency.
Say it again?
So you can't like make an argument that you can ignore the large frequency?
Oh, if you have like a band limit, a strict band limited, you could say you could ignore large frequencies.
No, but under your, whatever, the extension of band limit.
Like doing a Gaussian thing? You could make a claim that you could ignore large frequencies out to a certain point, but you still have a continuum of frequencies in
the
between,
continuum
like,
is what you're referring
yeah,
to.
the continuum, yeah. And then your time domain is also a continuum. So it's not like, yeah, fundamentally, this is the problem we're trying to solve, and I need to discretize this problem in some way to be able to actually solve it on a computer. So my goal is to discretize the problem. When I sample time points, that is what I'm doing. I'm just like discretizing this regression problem by restricting the number of rows in the regression problem. You can think of it as I had this super tall matrix where I was trying to fit a function for all values of t between 0 and big T. But I sampled some of those values, so now I have a much shorter matrix, a finite height matrix, that I want to solve the regression problem over. Yeah?
Just the time points, is entirely the simple points in the signal?
Yeah, exactly. These T1 through TQ are the points that I will sample from my signal. We don't know how we're going to pull this sample yet, but I'm just encouraging you to think about sampling the signal as sampling this regression problem we're trying to solve. So that's how we discretize the time domain. Then there's this question of how do we deal with the fact that the Fourier domain is continuous. And I claim that for like almost all constraints, almost all power spectral density constraints you see in practice, you don't actually need to deal with this. You can reparameterize your regression problem in a way that avoids it. So I want to sort of go blow through the details of this because it doesn't actually matter that much. What we're going to care about is how to sample time domain. But I'm going to at least quickly show you how we deal with the fact that there's an infinity of frequencies that we're trying to optimize our regression problem over. The way we handle this is you reparameterize this regression problem. You can show that it's fine to put an unweighted Fourier transform. G will always take the form of an unweighted Fourier transform times a signal z, versus z is actually defined on time domain. And then this outer product is equal to a kernel matrix. So it's a Q, but this product gives you a Q by Q matrix, K. You can rewrite the problem in terms of this finite Q by Q matrix K, and you'll get exactly the same regression problem. And the entries in that kernel matrix K are going to be exactly, you take the Fourier transform of your power spectral density, so that's what this term is, and the entry is just that Fourier transform applied to Tj minus Ti. So this is indexed by all of my sampled points, T1 through TQ, and this is like the standard kernel matrix you would see in machine learning, where every entry is a function of the difference between Tj and Ti for each pair of Ji. And that function is exactly the Fourier transform of your power spectral density. So this takes a minute to work through on paper. It doesn't actually matter that much for the results we're going to show. But what it means is that for basically all standard constraints that you can give me, we can avoid dealing with this Fourier domain continuity, because these things have closed form Fourier transforms. Like for the band-limited functions, your Fourier transform is a sinc kernel. For Gaussians, it's the Gaussian kernel, and as I mentioned earlier, for the Lorentz prior, it's the exponential kernel. So at least for standard shifting, scaling, mixing these things together, we can always get a closed form for the Fourier transform, so this regression problem is tractable as long as we know how to sample time domain.
So what is the order of quantifiers here? So there is a signal.
Yeah.
You decide on a set of points, and you want a set of points that works for every signal, or you want a distribution on sets of points?
We're going to get a distribution on a set of points that works for every signal. Really, I could imagine doing something adaptive where I look at the signal and use this to choose what points I sample. I guess we'd be happy with that too, but what I'm going to give is a distribution on a set of points where if I sample those points with high probability for some fixed signal, I'll be able to obtain that objective of getting y tilde close to y.
But did you say that the distribution is independent of the prior?
It's independent of the prior. It's going to be independent of everything. It's just going to be, it's independent of everything about the problem. The only thing it depends on is the sample size you're going to take. Okay, so how do we select points in time domain? It turns out that this reduces to problems that we've already learned how to solve very well for discrete matrices. So this is just the question, it's exactly the same question of forget that frequency domain's continuous. If I just had a discrete regression problem, how do I sample rows from that regression problem to get a good approximate solution to the original regression problem? You can solve these problems by sampling by what's known as a sensitivity function. So all this is on the top, I have the contribution to my error term, this entire error function, from one point t. And on the bottom, I have the entire error function. So it's the contribution that that point makes to the error function, and it's the maximum of that over all possible functions g. So a point's important if in a lot of potential solutions, it could contribute a lot to the error. Or not in a lot, if there is a potential solution, I suppose, where it could contribute a lot to your error. So actually, you don't need to, it turns out you can get prove things about sensitivity functions without worrying about your output parameter vector y. It suffices to sample points by a distribution that just depends on the norm of f mu star of g divided by the average norm plus an energy term depending on g. OK, so we're going to revisit exactly what this means later, but we'll get to it pretty shortly. What I want to mention is that if you sum up these sensitivity scores for a regression problem, you get what is known as the statistical dimension of the regression problem. And if you can sample by these sensitivity scores, you'll need to take statistical dimension samples to solve the regression problem. There's sort of a standard concept in like machine learning theory. I don't know a strict lower bound that you need this many samples, but roughly it's sort of what we believe the number of samples you need to solve a regression problem is.
Sorry, could you say it in
Yeah.
words? What was the statistical dimension?
So the statistical dimension is going to just be the sum of these probabilities that I need to sample data points by.
No, just the definition of statistical dimension. Just
Yeah,
in words.
yeah. I'm going to say. Well, I'll give it on the next slide actually.
Okay.
So what the definition of statistical dimension is you can work through what that sum is. It's like a certain trace of your linear operator. Roughly, it equals to the number of eigenvalues of your like weighted Fourier transform matrix that are greater than epsilon. So statistical dimension is parameterized by epsilon because we require more samples to get a higher accuracy solution. And roughly, you should think of it as the number of eigenvalues of that regression matrix I had that are greater than my parameter epsilon. Okay? And this lines up, like people have proved a lot of bounds on statistical dimension for these continuous function fitting problems just because it's sort of mathematically interesting. And this started with this work of Slepian and Polak. It matches up with sort of all of the expected sample complexities for these problems, but the only places where we provably know how to match statistical dimension in this parameter, this case I'm talking about, is for band-limited functions or sparse functions. Okay, so yeah.
These are eigenvalues, or the eigenvalues of f mu or f?
Technically, the eigenvalues of this operator f mu star times f. That's a positive semi-definite operator. Yeah. Yeah, that's a little weird because it sounds like it's unsymmetric, but it's because when I define f mu maps between two different L2 spaces. So if you sort of write that down, it works out.
Similar to a place semi-definite one, or?
It's truly like f mu star f, I believe, is truly positive semi-definite. Yeah. One way to think about this is you could have, for continuous distributions, you can take a square root of the distribution. Instead of making f mu times f mu star f, you can put the square root of weight on either side.
Sure.
So it's just like symmetric.
Is f mu a diagonal times f, or f times a diagonal?
F mu is a f star times a diagonal. Yeah, because it's reweighting columns. Okay, so if you sample by sensitivity, you can match this sort of like statistical dimension sampling rate, which for all the problems we care about sort of is the number of samples we want. Like you hit ft for band-limited functions, k for sparse functions, the natural parameters for Gaussian priors. The trouble is, like, how do we actually sample by sensitivity scores? They're not something we know in advance. And in general, they're very hard to compute. So there's been a lot of work in sort of more like discrete algorithms land on trying to understand how to very quickly compute sensitivity functions for discrete problems. So if you've heard of like effective resistances for solving graph Laplacians very quickly, or leverage scores for fast numerical linear algebra, these are the same as the sensitivity functions I defined. We care a lot about algorithms for computing those sensitivity functions very, very quickly. In our case, we don't even have that luxury. So it's not even really well defined to say I want an algorithm for computing sensitivity scores, because it's a continuous function. So I'd have to do something pretty crazy, like represent points of this function, figure out some approximation to it. So we don't even try to find an algorithm for computing these sensitivity scores, which would be sort of the adaptive version of this problem. We're going to do it non-adaptively. All we're going to try to do is use the structure of our problem to prove some upper bound on this function that doesn't depend on our inputs, it doesn't depend on our prior at all. And surprisingly, it turns out you can do this and you can still get something that very, very closely matches this sensitivity function. Okay, so let's revisit what this sensitivity function is. I'm going to ignore this regularization term for now just to make it a bit easier to understand. What it's saying is that this is some function, f mu star of g, is some function that was formed by my weighted Fourier transform. So if my weights was like the band limiting weights, it's some band limited function. And all I'm saying here is that I want to bound for every point between 0 and t, I want to bound the maximum value of the function squared over the average value of the function squared. So I'll look over all band limited functions, and if there exists some band limited function where at point t it can be much, much higher than its average value, then I know that's a point I want to sample more. So this is a very natural quantity that comes up in all sorts of approximation theory questions. For polynomials, you might have seen this before. So for a polynomial, I want to go back to that. There's something known as Markov brothers inequality. You can actually prove a simpler, there's a much simpler version of it if you're just trying to do this max over average, which says that if I create like a degree k polynomial, which is some relatively smooth function, at the edge of the interval, the maximum value of the polynomial could be as large as k squared times larger than the rest of the polynomial, the average value of the rest of the polynomial of the interval. But it can't be any larger than that. This is maximized by Chebyshev polynomials. And then there's something stronger known as Bernstein's inequality, which says that, okay, instead, I don't want to make my polynomial jump at the edge of the interval. I want it to jump in the center of the interval. Then you can't even make it jump that much. You can prove that the maximum value of the polynomial over its average value is it's almost k times its average value. Okay? So this means that for polynomials, you get a really simple bound on the sensitivity function. You know that across your interval, you sort of have this behavior where, I guess I didn't, yeah, sorry. So dead in the center of the interval, you can't do better than k. But there's sort of like a smooth transition to the edge of the interval. And that transition is you depend on like 1 over your distance to the edge of the interval. So it's just linear 1 over the distance to the edge of the interval. So you get a plot that looks like this. And this is exactly why, like, when people are interpolating polynomials, they're not using uniform interpolation nodes. They're using Chebyshev interpolation nodes. Because Chebyshev nodes, sure, it's a deterministic scheme. It's not random sampling. But it's concentrating more samples towards the edges of the interval in correspondence with the sensitivity function. And that helps you avoid having problems with fitting functions, like this phenomenon where if you use uniform sampling, you'll do very, very poorly on the edges of the intervals. So for polynomials, what is the sum of our sensitivity functions? What is our statistical dimension? In this region, really close to the edge of the interval, let's just take that region to be width 1 over k. Then we'll get a contribution of k to our sensitivity function. And now if we look at this region here, sure, it's like increasing up to k squared, but it looks like an integral of 1 over x down to x is like 1 over k. So we just get a log dependence on that. So the integral of that region is k log k. So we get a total sum for our sensitivity functions, a total bound on our statistical dimension of k log k. It turns out, that's just a brief aside. So you can already use something like this to prove sampling bounds for band-limited functions. So you can recover like all of Slepian, Pollack, Landau's work from the 60s on prolate spherical wave functions using sensitivity bounds for polynomials. But we want to do something more. What we're going to actually use is very, very similar sensitivity bounds for sparse Fourier functions. It turns out that essentially exactly the same statement is true. So if I take a sum of k sine functions, or just like k complex exponentials, it also can't jump too much near the edges of the intervals. And the amount that it can jump gets better as I get towards the center of the interval. So in particular, I can bound this maximum over the average by k to the 4th at the edges of the intervals. It was a little bit different before we had k squared. And then in the center of the interval, I get the exact same bound where it's k, and then it's increasing linearly as I get close, inverse linearly as I get close to the edge of the interval. OK, so I'm not going to go into the proof of this. It was proven very recently in this paper by Chen, Kane, Price, and Song. Roughly, the intuition is that when you have a k-sparse function, if your frequencies are far away from each other, you sort of have like orthogonal sine functions. So you can't really add them up in such a way to create places where the function jumps very high. And then on the other hand, if your frequencies are really close together, you have, if by like Taylor series approximation, your sparse Fourier function essentially looks like a low degree polynomial. So you can port over all the machinery from the low degree polynomial case. But it's not a super satisfying answer. It's also like a really nice question is, can we get a more direct proof of this result and tighten it? Because probably k to the fourth isn't tight. We believe k squared is tight. But anyway, we're sort of getting close on time. I'm just going to give you a flavor for what our contribution is. What we do is show how to take this result for sparse Fourier functions and translate it into a bound on the sensitivity for any prior on the power spectral density. And the way we do this is by using some other tools from matrix sampling. One of sort of the lessons we've learned in like the past 10 years of research on randomized linear algebra is that if I want to approximate a matrix with a low rank matrix, I usually do this by finding the top k singular values of that matrix. You can always pretty much find, or you can always, not even pretty much, it's just a true statement, there's always order for any like q. If I want to get a q rank approximation, instead of projecting onto the top q singular values of the matrix, I can project onto the top order q, like onto a certain order q columns of the matrix and get nearly as good of a low rank approximation. So I can always approximate matrices by a subset of their columns by projecting onto a subset of their columns instead of their singular vectors. And I get pretty much as good of a low rank approximation as I would have done with the actual singular vectors.
It is not a uniform sample.
It's not.
Answer.
Yeah, so actually for our result, we're not even going to care about how you get it. We just need an existential result that this is true. So once you have an existential result that this is true, that I can get a good low rank approximation for my matrix using some subset of its columns, then I can write my weighted Fourier transform matrix as some subset of its columns times a reweighting matrix. We don't even care what that matrix is. And it will be a good approximation. I'm writing epsilon, meaning I'll give you specifics on what that means, but it will be basically, if I take order S mu epsilon entries or columns in this matrix, I'll get an approximation that's pretty much as good as if I took the first S mu lambda eigenvector, or singular vectors of F mu star.
So this is with the optimal reweighting?
There's complex algorithms to do this. There's faster algorithms that lose parameters. We just care that it's in existence. And this is with the optimal reweighting. So if you find the columns and do the optimal reweighting, you'll basically match what you would have done with the best S mu lambda epsilon rank approximation. But as I said, S mu lambda is really the number of eigenvalues. S mu lambda epsilon was sort of like the number of eigenvalues greater than epsilon in my matrix. So if I take that many columns, it means I get a very good approximation. I get rid of all eigenvalues except those that have value less than epsilon. So I get a residual out that just has small spectral norm. And this lets me bound my sensitivity scores for the weighted Fourier matrix. Because I can basically say that when I look at the weighted Fourier matrix times some weights on frequencies g, I'll get something out that looks like a sparse Fourier function. And then the error will be epsilon times the norm of g. So what my goal was to do was to bound the maximum of that f mu star g over its average. This basically looks like the maximum of a sparse Fourier function over its average with some noise added to that, added to the average and possibly added to the maximum. But that gets washed out by that regularization term we had. So we can basically directly transfer over the bound we had for sparse Fourier functions to whatever weighted Fourier transform we wanted and we'll get exactly a number of samples that we'll be able to use this exact same sampling distribution. And just like we did for the polynomials, when you analyze the total number of samples you would get from a sampling distribution like that, it's just like S mu epsilon times log of S mu epsilon. So you match the statistical dimension up to a logarithmic factor. Okay, so that's sort of the punchline. The algorithm you get in the end is super simple. All you need to do is sample points by this fixed distribution. You don't need to, all you need to do is give me some number I want to sample of samples, sample by this distribution, build that kernel matrix using the Fourier transform of your prior, and then solve a kernel ridge regression problem. And then once you have the solution of that problem, it's very easy to quickly spit out values of y tilde t for whatever t you want. So that's the whole algorithm. What I want to mention at the very end is there are a ton of open questions here. So the first one that I'm very interested in is our algorithm looks over an interval 0 to t, and it like takes samples, and then it does a global reconstruction where it solves this big ridge regression problem. It's Q by Q ridge regression problem to get my final function approximation. We'd like to know if you can do it in sort of a streaming way. For band-limited functions, there's ways to do it in small space where you don't need to look at all of your samples, but it's not clear if you could do anything for general priors on the Fourier transform. Another really interesting question is, we're doing non-uniform sampling because we have this problems with the ends of the intervals. So the only reason we do non-uniform sampling is because this weird thing that polynomials, sparse Fourier functions, Gaussian weighted Fourier functions can jump a lot near the edges of intervals. So that means we have to sample a lot of points there. But maybe you could avoid this with simpler methods. Like maybe I can just do uniform sampling over a slightly larger range than 0 to t and show that I get a good approximation instead of having to do this somewhat more complicated non-uniform sampling scheme in the interval.
Doesn't it follow from what you already showed?
It doesn't necessarily, because like, so if I wanted to like say solve the problem just on a larger interval, it's not clear that like the Fourier transform energy to get that full function, it's not clear how to continue the function in such a way such that it has like the same I guess you could. Yeah, I didn't think about it, but I don't think it follows directly.
No, maybe not the exact bounds, but I mean, in general, that's the case, right? That if you have samples from a certain interval and you only want guarantees for 90% of the interval, it's
Right.
much better, right?
It should be much better.
No, but they are resolved.
Yeah, you just mean like generally. Yeah, I certainly believe this is true.
Just a precise bound.
Yeah, but if we want to get a precise bound like we have, I'm not sure it holds. Okay, and then another question, like sort of big question is, you can think of this as just giving an optimal sampling strategy for any sort of continuous function fitting problem you're doing. So people study optimal sampling strategies in geosciences. I want to sample points in a reservoir to know the general depth of the reservoir so I know how much water's in there. This gives you a sampling strategy, but it doesn't deal with any sort of constraints. So in geosciences, they deal with constraints. I can't go into that area because that's private property. I can't go here because of this. We would like to understand is there any way to naturally define like a cost function on the samples we can take, and then try to adapt these methods to giving optimal sampling strategies under some more complicated cost function when I'm not just allowed to take any point in the interval.
I can't go there because it's water.
Yeah, can't go there because water. So any questions? That wraps it up.